Morning, everybody. My name is Jörn Behrens. I'm one of the long-term visitors here at the Newton Institute for the Multiscale Atmospheric Whatever program. And I'm happy to introduce Nicole Beisiegel, who's a PhD student of mine and working on the gene methods for inundation problems. And yeah, Nicole, please.
Thank you, Jörn. Thanks for the nice introduction. Good morning, everyone. Thanks for the opportunity to talk about what I do for my PhD thesis. What I basically work on is an adaptive DG inundation model. And this is joint work with Jörn Behrens, who is my supervisor. So what I first want to tell you is the application that we have in mind that should be the outcome that when I finish my PhD, we want to have some sort of simplified storm surge simulation. Storm surges in general is like wind stress moving water to the beach or to the coast and wetting coastal areas. Especially for Hamburg, this is important because some of you might know that in '62 we had this severe storm surge event, and even today it's in the people's minds that there was this big event. And it's also sort of related to climate change because there are studies going on investigating whether the number of severe storm surge events in the German Bight, for example, will decrease or increase. And if you have a look at the paper Vote It All from 2001, it suggests that it's very likely that the number will increase. So we believe that having a model that is able to accurately simulate storm surges could be necessary then. Okay. Now I want to show you my equations, or the equations that we use. These are the depth integrated two-dimensional shallow water equations, which I wrote just here. It's du by dt plus the divergent of a flux tensor equals a source, so it's a balanced law. And for these types of equations, we need initial and boundary conditions, which I just wrote here. Maybe just to tell you a bit about my notation, with phi I always denote the geopotential and phi times use the momentum. These are the unknown functions that I, for right now, I just assume to be bounded. Here you find just shortly the notation of the flux tensor and the source term. What we consider is the advective flux, then pressure gradient forcing, and the viscosity. And as source terms, we have Coriolis forcing, which I denote with F. We have bathymetry forcing and wind stress, and also bottom friction that I denote with gamma. So let me start with the model details. Jörn already said we work on adaptive DG models. So what kind of adaptivity are we using? We're basically using H adaptivity. We use an adaptive mesh, it's spatial adaptivity. And we do that with a mesh generator called Amatos, which had been developed by Behrens and colleagues in 2005. And what it does, it creates a triangular mesh. I mean, you give an initial triangular coarse mesh into the generator and tell the number of refinement levels, and then what you get out could look like that here. This is for the Indian Ocean. That was in the PhD thesis of Widodo Pranovo. And then one other feature that we use is we don't want to have hanging nodes. Amatos takes care of that. I mean, we saw in Michael's talk last week during the PDs on the sphere that it is possible to have hanging nodes, but it makes computations a bit more complex because you might have to interpolate onto the edges if you don't have conforming elements. Another feature that we like to stress that you might have already seen in Michael Bader's talks is the space-filling curve ordering of elements. That's something that just comes out by the type of refinement that we choose. It comes nearly for free, and it assures that local neighboring triangles are also neighbors in the memory, which reduces the number of cache misses and should speed up the computations, therefore. Okay, some few details on the refinement. I already said we refine by bisection along the largest edges. And then there is also this strategy of resolved patches, meaning that first we refine according to some indicator that we can choose or determine, and to avoid hanging nodes we might need to refine some other triangles. And yeah, then I put that statement here. I think that an adaptive mesh can just be as good as its refinement indicator. So I believe that especially for realistic simulations that I work on, or that I will work on for my PhD, we need a good refinement indicator. Right now I just use these error proxies, like very simple criteria like gradients of sea surface height. But we also had a diploma student, Teresa Beck, you might have seen her talk. I think she worked with more physics-based criteria, and we also have another PhD student in our group, Susanne Beckers, who will work on more mathematical error estimators and maybe residuals of some operators. Okay, let me tell you a few things about the discretization of the equations. On top of this page, you again see the balance law with UH. I denote the numerical solution to this law. And we do the Galerkin ansatz, which means that the residual is orthogonal to the function space that we choose. In our case, we choose a space that consists of linear polynomials, for example, or on polynomials on triangles piecewise. So we don't want to have global discontinuity because it's a DG method. We also allow discontinuities over the edges. And then what comes out is exactly that formulation, which just is the statement that I wrote down here in formula. And if we then decompose the domain and then we do something that you might have seen in a paper by Giraldo and others from 2002, they do basically partial integration of the flux tensor twice, and then they get something that looks like that. That's the strong form of the partial differential equations. Also, one other step that just went in here is that we assume that also our unknown quantities. So where these integrals come from is one's from the orthogonality and the others from the basis function expansion. And what we then see here is basically an ordinary differential equation, because all these space integrals can be solved exactly using, for example, an interpolatory quadrature, like we use these Gauss-Lobato quadrature. So finally, we end up with an ODE, and that we solve with an explicit Runge-Kutta scheme. Then there's one issue that especially comes up, I think, when one does wetting and drying or storm surges or whatever one wants to call that. It's that it is known that just linear monotone schemes can be at most first order accurate. That's a theorem by Godunov from '59. But if we want to go for higher order, we might produce oscillations in the discontinuities. So we need to do something about that to fix it, to remove oscillations that are unphysical and just basically created by the numerical